Okay. That's how I get the secret thing from get-go, because I saved it as a mathematical template. So everything comes. Now we're going to test this, okay? If you have a function that you created but you haven't used before, you're not exactly sure what the input order are, and especially when you're using it for the first time, just to make sure that it works, go to that little function helper, fx, and go to user defined. I don't know why there are so many Dutch stuff here. And just find your function, fixed bond price equals, or okay. Now I can enter my inputs. My coupon rate, right here. You could also write a little help file, but I'll do that in my Excel workshop. Yield to maturity, IFACE, ITIME. ITIME means in an hour in Norwegian. ITIME, where is it? Years to maturity. And IFREC. Done. Apparently I made a mistake. Instead of double, I said dupke. There is no data type called dupke. So let's change that to double. Close this back. Oh, I should have said dim. Any dim statements have to come before you make any other calculations. And what do you know? In fact, let's calculate the exact difference between them. It's precisely 0. At least the way Excel shows it. I can add digits to that. Nothing. Let me make it a general number. Still 0. So it's not even different by what we call in computing the machine epsilon. Machine epsilon is such a number that if you add a number less than machine epsilon in absolute value to 1, computer gives you 1 as the answer. That's roughly 10 to the power negative 15 or so. But certain calculations requires a lot of precision. Since we have only 7 minutes left, I'll tell you the story. Have you guys ever heard of something called fractals? Okay, let me show you a picture. This picture is obtained using only mathematics. Actually, I'll show you the more, I'll show you this simple one first. This set is called the Mandelbrot set. Come on. Do you see the beauty of the picture? There's not a single artist's hand that actually touched the picture. It is entirely generated using computer code. And here is how it is done, roughly speaking. Consider following simple equation, z cubed equals 1. But z is a complex number. That means z is equal to some a plus ib, where I is equal to square root of -1. That's called an imaginary number because there are no real numbers that has -1 as their square root. But this sort of stuff is rather useful in physics, in integration of some complicated stuff. There are 3 solutions to this equation. One of them z equals 1, and the other 2 are complex conjugates. I don't remember the exact number, but so let's call that z1. z2 equals a plus ib. z3 equals a minus ib. So if you know what a and b are, those are the solutions. That's fine. In general, when you have equations like that, there's a little method called Newton's method. You start with an arbitrary guess. So let z0 be an arbitrary guess. Then it's called a tilde for solution. Z tilde t plus 1. You start with a current guess, and you're gonna make a you're gonna make a distinction between the two. This would be an iteration of Newton's method. The top is the function minus right-hand side. The bottom is the first derivative of the function, evaluated at the current guess. For well-behaved function, this actually converges to a solution of the equation very fast. If you're around the solution, convergence is quadratic, which means the number of correct digits in the answer doubles every time. There is a more complicated one. It's called Halley's method. I'm actually writing a paper on that, on how it helps emerging CDFs and stuff. That has cubic convergence. If you're close enough, correct number of digits triples every time. In fact, sometimes you just come up with a rough solution using a cheap method, then you use Halley's just once or twice to polish that solution. Anyway, you're thinking, you do this, the answer is, and you're going to do this in the complex domain. There's no reason you cannot cube a complex number. The solution, this process is going to converge. It's going to do one of 4 things. It's going to converge to the first root, which is 1. It's going to converge to the second root, a plus ib. It's going to converge to the third root, a minus ib, or it's just going to explode. It's not going to converge anymore. That is possible. Unless you safeguard the process, that can happen. So you're going to tell your computer to do the following. If the damn thing explodes, start with a starting value, picked randomly. If that leads to an explosion of the algorithm, basically say, after about 20 iterations, Z is in billions, we probably are not doing anything. And do a little two-dimensional graph. On the horizontal, you have the real value, real part of the number, A, for example. On the vertical, you have the imaginary part. And if it explodes, paint that pixel black. If it converges to the first root, paint that pixel blue. I don't know. Converges second root, red. Converges third root, yellow. You pick your own colors. And you do this for a lot of numbers within a certain range. Let's say plus or minus 2 on the real and the complex side. And as you do this, picture kind of appears. This is going to be one of those pictures. Okay. And the funny thing is, if you can see this major pattern here, okay, it also appears on the edges. In fact, if you are able to zoom on those, you're going to see that the same pattern repeats itself. In fact, it doesn't matter how much you zoom, if you have the ability to pixelate those zoomings, the exact same pattern is going to appear, and there's no end to it. In mathematics, these sets are said to have fractal dimension, or fractal Hausdorff dimension, which is a very precise definition of dimension. You view this as a two-dimensional picture, but it has a Hausdorff dimension of, I think, 1.7. It's not exactly a two-dimensional object. Okay? And you may have 2 points that are very close to each other, and you start from one or the other, they're going to converge to complete a different stuff. That's called a chaotic process. Okay? Have you guys ever heard the expression butterfly effect? A butterfly flaps its wings in Amazon, you get a tornado in Kansas. You know, little things can create huge consequences. Anyway, I'll see you guys on Thursday. We're gonna actually write code for duration and all that other fun stuff.